Hello friends. You put on a pair of headphones, press one button, and the roar of the world just disappears. How does that actually happen? In this video, we are going to answer that question, and the answer turns out to be calculus. In February 2026, Sony launched the WF-1000XM6 earbuds, powered by a new QN3E noise-canceling chip. Then in April 2026, SoundGuys published hands-on impressions of its scene-based listening feature, where the earbuds automatically adapt their cancellation to your environment in real time. That kind of instant intelligent silence does not come from magic. It comes from a very specific loop of mathematical operations running millions of times per second. Let us trace that loop step by step, starting with the most basic question: what exactly is sound? Alright, before we can cancel sound, we have to describe it mathematically. Sound is a pressure wave. As it travels through the air, it alternately compresses molecules together, and then pulls them apart. We can model that as a continuous function of time. Call it f of t, where t is time and f gives the air pressure at your ear at every instant. The peaks of that function are compressions, the troughs are rarefactions. Quiet background noise, like the hum of an airplane cabin, is a fairly regular, repeating wave. That regularity is exactly why calculus is the right tool to work with it. Once we have noise expressed as a smooth, continuous function, every concept from your calculus course becomes available: derivatives, integrals, optimization. The derivative is where we start next. Now here is the interesting part. The headphone's digital signal processor, the DSP, needs to understand the shape of the incoming noise wave instantly. It does this by computing the derivative. The derivative of f of t, written f prime of t, tells you the instantaneous rate of change of the pressure wave at every moment in time. A steep positive slope means pressure is rising fast. A slope of 0 means you are at a peak or a trough. By reading f prime of t, the DSP can identify the wave's frequency, its amplitude, and where it is in its cycle, all without waiting. In the Sony WH-1000XM6 headphones, the QN3 chip processes 12 microphone inputs at once to do exactly this. For the WF-1000XM6 earbuds, the QN3E chip achieves the same in a much smaller package, with 4 microphones per earbud. Speed matters. The whole analysis must complete in microseconds. So now we know the wave's exact shape. What does the DSP do with that knowledge? It multiplies the wave by -1. That simple operation flips every peak into a trough, and every trough into a peak. The result is the anti-phase signal, written as -f of t. Here is the core identity: f of t plus -f of t equals 0. +1 plus -1 equals 0. When the original noise wave and the inverted anti-phase wave meet at your eardrum, they cancel each other through destructive interference, and the result is silence. The headphone's driver plays the anti-phase signal in real time, and your ear hears the sum of both waves, which is effectively nothing. This is why ANC typically reduces background noise by 20 to 40 decibels, cutting perceived noise to as little as 1/16 its original level. One equation, elegant and powerful. Here is where calculus goes one step further. Phase inversion works well, but real environments are messy. A coffee shop sounds different from an airplane. The anti-phase signal is rarely perfect on the first pass, and a small residual noise, called the error signal E of t, leaks through. The FXLMS algorithm, which stands for filtered x least mean squares, handles this. It defines a cost function j as the integral of e squared of t over time. That integral measures the total accumulated error energy. The algorithm then uses gradient descent, moving the anti-phase filter's parameters downhill along that cost function to make j as small as possible continuously. This is textbook calculus optimization, applied in real time. Inside the Sony WF-1000XM6, the QN3E chip runs this loop millions of times per second, tuning the cancellation to every new environment almost instantly. The math never stops adapting. Let me show you how neatly this all connects. Every time you press that ANC button, 4 calculus-driven steps fire in sequence. 1. The microphones sample the ambient pressure and model it as f of t. 2. The DSP differentiates f of t to read the wave's shape and frequency in real time. 3. The signal is multiplied by -1, producing the anti-phase wave -f of t. 4. The FXLMS algorithm integrates the squared error and uses gradient descent to refine everything continuously. Those 4 steps, sample, differentiate, invert, adapt, are derivatives, integrals, and optimization working in perfect coordination. The Sony WF-1000XM6's scene-based listening feature, highlighted by SoundGuys in April 2026, runs this same loop whether you are in a cafe or on a train. So next time a pair of headphones goes quiet around you, here is your challenge. See if you can spot the next place calculus is quietly running in the background. It is probably closer than you think.